Hi guys, so today I'm going to start with the practical sessions in which the starting data set that I've taken is the iris data set, which is a very common data set. Okay, so guys, without further ado, let's start. Okay, so in this video I'm going to show you the basic pre-processing that's going to be done. Okay, in that I'm going to cover the check of the nulls or the NAs. Then I'm going to show you the how to check on the dimensions of the table, uh, and to check that what is the data that you have, then to see what the class of the data is, then the distribution of the data, in summary, and some other statistical important data points that we have. Okay, and this is going to be a bit crucial because to understand that what algorithms you need to give, what transformations you need to do, you first need to get to know your data. Okay, you have to be very familiar with what the data is, what its structure is, what its capacity is, how it looks like. Basically, with the look and feel of the data is very much important. The feel of the data you can get through this statistical analysis, and the look of the data you can you can see through the graphical analysis that I'll do in the next video. Okay, so without further anything, let me start. So as you can see right now, it's a fresh RStudio that I have. Okay, in that, let me open a new file. In that, I'll open my script. Okay, so in that, so let's say I'm starting with the iris dataset. Okay, so in the console, I'll just put in data iris. Okay, so if I do the data iris, see the iris value comes over here, and if I want to see, so let me copy this data iris, because this data iris I will be using it a lot. Okay, next let me see what iris looks like actually. Okay, so this is what actually iris looks like. If you can click from here itself, you can see in the data frame that what actually it looks like. Okay, so you have the five columns called sepals, sepal width, petal length, petal width, and species. Okay, so next, let's see that if there are any null values in it or NA values. Let's first see the NA values. So for NA values, there is a function called is.na. Okay, so in is.na we have to pass in the object name. So here the object name is iris. Okay, because iris is the data frame that we have. Okay, so this is a data frame actually. This in the tabular form in the data, and this is contained in the frame. So it's a data frame. Okay, so now let's see if there is any NA value. So problem with NA is that it will check for each and every object. Okay, so to overcome this hurdle, what we do is we do a sum of over the is.na. Okay, so if there is a null value or a NA value, it will give a sum as more than 0, right? But now if I do a sum, see in the console I can see there is a sum as 0. It means there is no NA values. Similarly, if we do a is.null over the iris data set, okay, it will give us that it is not a null value, right? So that is how you check for the NA values and the null values. Okay, next, if I need to see that what it actually looks like. So if I can see obviously from here that it has 150 rows and 5 columns, but is that confirmed? So let's confirm it. So there is a function called dim which gives me a dimension of the data set. Dim of iris will give me 50 cross 5. That means this is the number of rows. 150 corresponds to the number of rows, and 5 corresponds to the number of columns. So similarly, you can check with there is something called as n rows and n columns. Okay, so with n rows you can check the number of rows. See, let's see n rows. So number of rows is 150. Similarly, if I give a n column function, n col with iris, I can get 5. So that means we have a matrix or a data frame with the value of 150 cross 5. Okay, so now that we know that the dimension is 150 cross 5, 150, let's do x and cross 5. That means this is the number of rows, and this is the number of rows, that is the number of columns. Okay, so now what does this data set actually give us? So let's suppose I do a help. Okay, in this you'll be able to get a basic information of what iris actually is. Okay, what this data set of iris actually is, what is it is going to tell us, what we are supposed to do with it, etc. Okay, so as you can see, it is saying that iris is a data frame with 150 cases of rows and 5 variables. So this is what again we also confirmed, and we could see that these were the names of the rows of the columns that we had. Okay, so this is a two-dimensional matrix, you can say, while iris 3 is a three-dimensional. Okay, so next is some you can say an example of how to use this data sets, etc. is given in the examples, just to give out an assurance that yes, it is true, it can be used. So one small example is given using iris 3 data set, but we are not using the three-dimensional, we are using the two-dimensional. Okay, so now let's see that so now that we have calculated the number of rows and we know that what the number of columns is, we have checked, right? The number of columns is 5. So now after that we want to know that what is the value. That means suppose we can see from here that species is setosa, petal width is somewhere around 0.5, some are 0.1, petal length we also have values, petal weight, petal sepal length, sepal width, etc. But what is the class of each and every column? That is a very important factor that plays out because for analysis, because this is an important part. Is the column a float value? I mean, is it in suppose having only 0.2 or 0.1, or what are the values in it, and is it a categorical data, is it a numeric data, is it a floating point, like that. So this is actually helpful when you are doing the analysis part. So there is something called as the S apply. Okay, so when I do the S apply, what it does, it applies a particular function to each and every column in that X. Okay, so with S apply, let's say we give the iris data set. Okay, so let's see what S apply tells us. So I give here S apply with a question mark in the front. So this is how actually you check out that what a function actually tells you, with a question mark and followed by what the function name is. So the function that I want to know about is S apply and a question mark in front of it. And in the right hand side you can see that what it actually tells us, that, and you can see that okay, what are the values it should take, what are the parameters. It's a parameterized function, right? So what are the parameters it should take, right? So here is S apply. So X func simplifies true, usename is true. So X is basically a vector, func is basically a function that needs to be applied. Okay, so let's see now with S apply. So now we know that S apply takes a function. Okay, so iris is my data set and my function is something called as the class function. Okay, so class function will tell you that what is the class of each and every column. Okay, so here you can see that okay, sepal length is a numeric, sepal width is numeric, petal length is numeric, petal width is numeric. Species is something new which is called as factors. Okay, so what are factors basically? So in when you're doing a classification, right, you are dividing your data into specific classes, right? Suppose in this, if I will show you later that what are classes basically. So suppose when you go for gender, right, you have male, female, not to be disclosed, others, etc., right? So these are proper classes that you have. But suppose you go for age, or you go for say stock market investment, right? So you can't classify them. So so age is basically, so maybe I'm 25, maybe you're 26, maybe you're 10, maybe you're 15, maybe you're 30 even, right? Those are numeric values. You can't put them in specific classes. But suppose gender, right? Suppose whether you are qualified for this exam or not. So yes or no. So these are specific classes. So that is so these classes in are called factors. Okay, so that is how factors come into play. So in species you can see here these are factors. So that will give us an idea that okay, this is a type of a classification problem and not a regression problem. Regression problem are those problems which in the output is a numeric value, but in species it's a factor. That means it's a classification problem. Okay, so now the question arises that how are these classes distributed? Okay, and what are these classes? So let's see that. Let me define a vector called y. Okay, you will see that y is mostly used when you're doing the outputs of any data, etc. So let's see for y. So y will be my iris, and the column that I'll take for iris is species. Okay, now here you can see that factor with 3 levels. That means there are 3 basically distinct classes. Okay, so what are those three? Let's see. So we do a C bind. What is C bind? C bind is basically a binding with the columns. Okay, so in C bind we'll give two basic things. One is the frequency. Okay, in frequency we'll give the table of Y. Okay, let's see what table of Y actually gives us. Let's do a table of Y. When we do a table of Y, it will tell us that okay, Seto size 50, vesicolor is 50, virgin nica is 50. That means these three are 50, means each of these classes are 50 in numeric. This is a classic case of equal distribution of classes. Remember, it is not equal distribution of the factors. It is the equal distribution of the factors. It is not the equal distribution of the variables or the numeric things that we have. So we don't know that what these actually look like. Sepal length, sepal width, what is the classification, or how do when we plot it, we'll be able to see that what it actually looks like. But for now, we only have the information of the output variable. Okay, that setosa is 50, versicolor is 50, and virginica is 50. So that is classic case that in the classes are equally distributed. So it is almost never the case. Okay, so we always have imbalance. Suppose vetosa is 40, versicolor is say 10, and virginica is say 500, right? So this is an imbalanced data set. Okay, so right now we have a very good example of a balanced data set. This is actually a toy data set because we only have 150 rows, right? Let's see, let's practice with this. Okay, they're very good for practicing. Okay, so now we have the frequency is of a table. Okay, so this is the frequency. So now we need to know that what is the percentage that each of it will take. Obviously we can see from here that it will be 33%, but let's put this in a very good table. So let's see how it comes up. So we have something called as the prop table or the property table. So in that we'll just do a table of x, table of y basically, and we'll multiply it by 100 because we need a percentage. Let's run this part. See, right? I made a mistake somewhere maybe. Okay, so here you can see that it is 33%, right? So this is how you check that okay, in my table it is 33%. Wow, I think yeah. Right. In every programming language, just remember you have to be very careful with the brackets. So here I made a mistake with my bracket. That is why my percentage was coming as 0.33%, but that is very less, right? Okay, so that is why. See, I made a mistake. I took the 100 inside the bracket, which led to an error. So if I take the 100, see, it will be 33% each, which we can actually see, right? So 100 divided by 3 is actually 33.33%, which is fair enough, right? So this is basically saying that each of your class is equally important. Okay. Okay. So now we have information about my output variable or the predicted class. So now the question arises that what about my numeric variables? These four things like sepal length, sepal width, petal length, petal width. What information can I tell you about it? So one very good thing that R provides us is a summary function. So what is a summary function? Let's see. So when a summary function which I give with an iris, okay, so it will give me the minimum, the first quartile, the median, the mean, the third quartile, and the maximum. Okay. So basically now you can see that suppose you are plotting the graph, right? You will understand that if you suppose you give your value specifically, then you should know that what is my minimum of that, what is the maximum of that, what is the mean, what is the median, etc. Right? This actually is very useful when you are trying to fill your NA or null values. Okay, but it will also give you an idea when you are doing your say suppose normalization or basically variable change, right? Here we have four variables. Okay, sepal length, sepal width, petal length, petal width. Suppose you want to make more variables with a combination of these, right? Maybe a linear combination, maybe an exponential combination, maybe a non-linear combination. It's up to you. But when you make a combination, you should know that what these factors are going to means how these factors are going to change, right? So suppose I multiply these two, how are these factors going to change? How is is it going to enhance it? Is it going to degrade it? So this is again a trial and error method. Nothing is proven. Okay, you have to work it out. You have to get your hands dirty, as I say it. Okay, the summary will give you a very good idea of what the data set looks like, what is actually going on in the data set, etc. Right? But one thing that summary lacks is something called as the standard deviation. Okay, so for standard deviation, what we can actually do is again we go for the S apply. Okay, so again in S apply we again have so in S apply we did what? We did an iris. Okay, and then we, let's say we call the SD function, which is the standard deviation function. Problem is that iris itself has the factor, right? And you can't take a standard deviation of the factor. So now how do you solve this problem? Suppose I take only the first four columns, so 1, 2, 4. Okay, so now if I take only the first four columns, okay, so first one is row, obviously we have R and C, so row and column. So then I'll see, you can find here the SD or the standard deviation. So we can see that the least deviated is the sepal width and the most deviated is the petal length. So we'll be able to see in the graph that how this actually SD function is actually helping us in classifying them in a very good way. Okay, so when we come to the algorithms, when we come to the graphs, I'll show you that suppose I take only one of the columns, or which is the most influential column out of these four. This can also be found out. This is a very important topic that people sometimes don't give much importance to, because suppose one of your columns is giving the maximum importance or is actually the most functional in determining the output, right? So how means, so then yeah, common sense says that that column should be given the most importance, right? So then suppose you enhance that column. So there are techniques to enhance it. Do you just multiply it? Do you just do an exponential of it, or do you create your algorithm in such a way that only that column gets the most value? So these are all algorithms that will come at a later stage, but for right now we can see these are the numerical analysis which gives us that okay, this sepal petal length is a very important factor. Okay, because others are say less than 1 or very close to 1, but this is close to 2, that means the deviation is very high, right? So this is one thing that's again a very crucial when you do numerical analysis of the data set. Similarly, one more important aspect is your skewness. Okay, so similarly for skewness, we'll do an apply. So here we won't do an S apply, but we'll do a simple apply. So similarly here we'll do an iris. Suppose people will again say let's go for iris 2 and say skewness function. Okay, now why did I give a 2? Again, if you go to the apply and do a question mark, you'll be able to see that 2 here indicates the columns and 1 indicates the rows. I don't want to calculate the skewness of the rows because it does not make any sense. I need to calculate the skewness of the columns. Okay, so let's see that if I do just this, how much helpful is it? Here you will say, okay, I forgot something maybe. Okay. Okay. So here we have an error, right? That it says that skewness not found. Well, let's see why. Because one important thing is to know is that like Python, R also has certain libraries which needs to be imported, right? So skewness is part of a library called the ML bench. Okay, so let me import that. So we have a library called ML bench. Okay, we have to import that. So this, because I already had library ML bench installed, that is why I could just use library command. Otherwise, what you can do, a very easy solution is go to tools, go to install packages. Okay, and in this you can just do an ML bench. Okay, right. So see, my ML bench is already installed. It's going to install. See, it installed successfully. It will hardly take a few seconds. Now, if I do this, let's see what happens. Oh, still not found. Okay, maybe it's not in this. Maybe it's in another library called as E1071. Okay, it's not there. Let's install it. E1071. Done. Okay, so now let's use it. See, non-numeric argument to binary operator. That means iris has a non-numeric argument. We know that the non-numeric argument is the factor variable, right? So let's remove that using the same thing that we did a bit earlier, right? 1, 2, 4. See, now it gives us a skewness. So that means skewness, when we come to the graph, I'll show it in a better way that what skewness actually means. So let's imagine a perfect Gaussian curve. Okay, I have a very bad drawing, so just bear with me. Okay, so when we make a perfect Gaussian graph, say this is my x and y. Okay, and when I okay, when you talk about skewness, so this is called as the non-skewed graph. That means that the graph, the highest point of the graph actually cuts the y-axis. But suppose your graph lies somewhere here or somewhere here, then it basically is called as the skewed graph. Okay, sorry for the bad drawing. Let me remove that. Okay, so this tells us that none of this is a perfect Gaussian graph. Some are positively skewed, some are negatively skewed. So now it is our task to find out that should we unskew it or should we not unskew it, right? There are particular methods in which we can unskew it or skew it further. So then it is up to us whether we do something about the skewness or we don't do it. But this is one thing that I needed to show to you. Okay, this is one important factor that needs to be told. Okay, so then one more thing that comes into action here is the correlation. Now correlation can be between two things, the self correlation and the intercorrelation. Obviously self correlation of a variable with itself is always 1, but what about its dependency on the other variables? Let's see. So let's do a core function, core, then the data set, which is the iris, and then we gave the 1 2 1 2 4. Okay, so now what we got, see, sepal length with sepal length is always 1, sepal width with sepal width is 1, sepal petal length with petal width is 1, and petal width with petal width will be 1. But if you see, so take either the top half or the bottom triangle or the top triangle. That is how you can be able to see that what it actually looks like. So this is a symmetrical matrix, right? So here you can see that the petal length and petal width. Okay, so if I come over here, see petal length and petal width, so they have a very high correlation. That means with an increase in either the petal, with an increase in the petal width, the petal length also increases. With a decrease in one, the other also decreases. That means there's almost a close to 1 relationship. Similarly with sepal length and petal width, so there is almost a close to 1. That means again here comes a question that should I consider both these factors or should I do something which is called as reduced dimensional reduction. Okay, so here I have 4 major things. Can I reduce my data values? Can I reduce the number of columns that I have? Here I have 4. Can I make them 2? Can I make them 1? Can I make them 3? How will it impact my analysis? How will it impact my output of the algorithm that I'm going to deploy? So this is another important part of your numerical analysis. So this is actually how you do your numerical analysis. This is just a small introduction that how you do your numerical analysis. In the later videos, next video that's going to come up, I'm going to show you that how you can transform all these numbers and everything into very good graphs. Okay, so remember one thing, that in graphs there are 2 types of graphs that you can do. One is a tidy but informative graph. Second one is the informative, neat and clean but time consuming graph. So if you want to be a very good data engineer or a data scientist or an ML expert, then you need to make very quick decisions, right? So you can't sit back in your chair and make graphs which look fancy and which give the same information which a dirty graph can also make. I don't want any coloring, I don't want to give a very fancy drawing, fancy labels, etc. because I know the code, I know how it looks like, right? I can explain it. That is one graph that you should be typically looking at, is the dirty graph. Obviously, if you have your time, if your deadlines are say a bit further, obviously you can go for the graphs which are a bit fancy looking for their clients, but suppose you are in a time crunch. Okay, suppose you want to do it very fast. How do you do it? Make dirty graphs. Okay, well guys, I think it's all done for the numerical analysis part of this data set, because it's a very small data set, nothing more data I can extract from it right now. Okay, so next video that I'm going to make is I'm going to plot these in graphs. I'll show that there are various types of graphs: univariate or multivariate, box plots, histograms, whisker plots, etc., etc. So in that I'm going to show you that how these can be further seen in graphs and visually seen. Okay, because client is not going to look at all the data, customer is not going to look at the data, they are more interested in more visual things. One thing to show them, graphical method. Okay, thanks a lot guys, bye bye.